A very good morning to all of you. And today I'm going to move on because last time in the previous lecture, I talked about the Stern-Gerlach experiment. Because as long as our course is concerned, we have already taken into account the problem of hydrogen atoms, solved it for N, L, and Ml, and then we have been talking about the existence of an intrinsic property that's linked with an electron, and that intrinsic property is the spin of an electron. So based on the argument of spin, the existence of spin of an electron, we can generate a model of an atom, what we call as vector model of an atom, and this vector model of atom will give us the correlation. I mean, the interactions that can take place between the orbital motion of the electron and the spin angular momentum of the electron. But one thing has to be kept in mind at this moment of time is that the spin that we have been talking here is not the classical spin. It's not acting in the classical way, because in quantum mechanics we generally have no physical interpretations of the things. I mean, the physical, what I mean to say here is that what we understand in classical sense is not true when we think about the same thing in quantum mechanical sense. So we have a target of dealing with the vector model, of one electron atom. We have been talking about hydrogen atom, and as we know that hydrogen is the simplest of all, and being simplest of all, to analyze and to do the mathematical work on the simplest is always a good choice. So we have been in the domain of one electron atoms, and here what we have is we have an electron, and this electron is existing in the domain of the nucleus, and this electron has orbital angular momentum and it has spin angular momentum. So when we talk about the angular momentum is a vector quantity, and whether we have orbital angular momentum, it's a vector quantity, and we have the spin angular momentum, it's also a vector quantity. So how we demonstrate the vector model of one electron atom is that we take into account the existence of these two angular momenta. One is the orbital angular momentum of the electron, and which we already have calculated solving the problem of hydrogen atom, and we have obtained that angular momentum vector as its magnitude is under root of L times L plus 1 h bar. So this result we have already obtained. If we rightly go back to solving the problem of hydrogen atom, we have obtained this magnitude of the orbital angular momentum, which is quantized by introducing a constant in solving the Schrodinger's wave equation in spherical polar coordinates. If you rightly remember the problem of hydrogen atom, we have Schrodinger's equation, then we make use of variable separable approach, and in solving that equation we introduce some constants, and angular momentum is one among those constants that we calculate as a condition to obtain the solution of the Schrodinger's wave equation. So in demonstrating the vector model of this this one electron atom, what we have is we have vector L and we have vector S. And here we start by talking about the total angular momentum. Total angular momentum vector. And what we do is we symbolize this total angular momentum vector by J. And this J is basically the coupling of, because the original thing that we have in this 1s electron atom is it has orbital angular momentum and it has spin angular momentum. So when we couple the orbital angular momentum with spin angular momentum, we get the total angular momentum J. So if I assume that L is the total angular momentum of the electron, orbital angular momentum of the electron, and S is the total spin angular momentum of electron, which, by the way, we have demonstrated as a result where we can have only two states of the spin angular momentum for an electron, and one state can be plus half, the other state can be minus half. So what we have is we have the total angular momentum G, and this total angular momentum G is the vector sum of orbital angular momentum and spin angular momentum. Now, this is what we generally call as LS coupling. So you have the coupling going on in an atom, in one electron atom, and that coupling leads to the total angular momentum vector, which is also called as inner angular momentum of an atom, and that is symbolized as J, and L is the orbital angular momentum, and S is the spin angular momentum. Now, if I talk about L, now L is, if I write down its magnitude as L, so this L is already calculated as under root of L times L plus 1 h bar, where this h bar is the reduced Planck's constant, which is given by h by 2 pi. Okay, so we have the magnitude of orbital angular momentum of the electron in this one electron atom, and this L is the orbital angular momentum, and the small l is here the orbital quantum number. Now, if we set the given problem to be quantized along the direction of z, so if I have to write down Lz, then Lz will be ml h bar, and this ml is our magnetic quantum number. So this is magnetic quantum number. And the value of this ml, it will range from, the value of this ml will range from plus L to minus L, so that it leads us to 2L plus 1 discrete set of values for the magnetic quantum number. And so this is our orbital angular momentum, and we have written down it in terms of the orbital quantum numbers, and we can see the quantization of this angular momentum when we choose the direction along z, and you have only certain feasible orientations for the orbital motion of this electron that is dictated by this ml. And similarly, what we have is we have S as the total spin angular momentum, and the magnitude of this spin is S, and by analogy, we can write down this S as under root of S times S plus 1 h bar. where this S refers to what we call as spin angular momentum. Momentum quantum number. It's a quantum number. So, so if I choose S in the direction of Z, in that case, I will have Sz equal to msh bar, and this, because we know from Stern-Gerlach experiment, you can have two spin orientations of the electron. So the value of this ms, which should actually go from plus s to minus s, it leads to plus 1/2 and minus 1/2. So this gives us the measure of spin along the z direction, along the z direction. So what we have now, we have Lz and we have Sz, and we can immediately think about the total angular momentum. And what is our total angular momentum? That is given as j vector, and I can write down its magnitude as j, and it must be equal to under root of j times j plus 1 h bar. And if I choose the direction along the z direction, then this jz must be equal to mj h bar, and this mj, the value of this mj will range from plus j to minus j, leading us to the values 2j plus 1. Now what we have is, we started from vectors, we started from vector j, we started from vector l, and we started from vector s, but now we have been talking about the components of these vectors, say Lz, Sz, and Jz. They are now our scalars because we have them as components of the original vectors. So we will have a scalar equation. We will have a scalar equation, Jz equals J equals Lz plus minus Ls. All right, so what we have here is, we have a scalar equation. Now, depending on the orientation of the spin of the electron, this has to be Sz. This has to be Sz. So depending on the orientation of the electron, you can have a maximum Jz or you can have a minimum Jz, because in one case, the spin will be added when it is positive and it will be subtracted when it is negative. Now, if I write down my equation, what I have here is mgh bar, I can write down, is equal to ml h bar, I can write down plus minus ms h bar. And we can immediately see that these h bars can cancel, and we will have mj equal to ml plus minus ms. And we can know that mj, ml, and ms, they have a clear relation with original j, they have a clear relation with original l, and they have a clear relation with the original s. So that means we can have a situation here. We can have a situation where we can obtain a result based on the original total angular momentum, total orbital angular momentum, and total spin angular momentum. So from this equation, if I have to, if I take this as basis, this J, Jz is Lz plus minus Sz, and Mj is Ml plus minus M S. So one thing is clear here. What's that? That is that if we have the addition of the two vectors, we will have J. I mean, if I have a situation in which I have to add the two orbital angular momenta, the total J will have two kinds of situations. The first situation will be in which we will have J is simply L plus S, and another situation will be J will be L minus S. So in one case, I will have J. In this case, J will be in this case J, and if I have the relation between J and L, so if L so this is my J, right? And this J can be greater than L, and this J can be less than L, depending on the addition and the subtraction of L from the spin, because we understand in one case the spin will add to L, and in another case spin will subtract to L. And if we have to demonstrate this thing, we can think of, if this is my L and this is my S, okay, this is my S, this is my L, this is my S, and this is my J. So here I can say that J is greater than L. Okay, and if I have to represent a situation where the value of J is less than L, so it can be taken like this. So this is my L, this is my S, and this is my J, and J clearly is less than L in this case. Alright, so this is how we can demonstrate the magnitude of J. In one case it's greater than L, and in another case its magnitude is less than L, depending on the orientation of the spin with respect to the orbital angular momentum. Now, the point is, you have the orbital motion of the electron. Now, electron is a charge, and we understand whenever charge accelerates, it produces electromagnetic waves. Now, keeping that thing apart, now the motion of this electron is equivalent to a current. So when you have the motion of the charge, it demonstrates the current. So wherever we have current, we have magnetic field. So in our problem, what we have an electron. It has two kinds of angular momenta, right? That means it must have two kinds of motions involved in it. One is orbital angular momentum, and another is spin angular momentum. So the magnetism is originating from the orbital motion of the electron, and at the same time the magnetism is originating from the spin motion of the electron. Now what we have atom as a whole. So there is already an interaction taking place. There is an interaction taking place between the orbital magnetism of the electron and the spin magnetism of the electron. And this interaction between orbital magnetism of an electron and the spin magnetism of the electron leads to an interaction which is known as spin orbit interaction. So from here, what we obtain is the spin-orbit interaction. So there is interaction between the spin of an electron and its orbital motion, and both the motions are basically they are developing the magnetic field. So there is magnetic interaction, and this magnetic interaction leads to what is generally known as fine structure of hydrogen atom. If we go back to the model of Sommerfeld model of Bohr-Sommerfeld model of hydrogen atom, they failed to explain the splitting of spectral lines. They failed to explain that in the cases where the value of small l, which is orbital quantum number, is equal to 1. There is splitting. The Bohr-Sommerfeld theory completely fails to explain that that splitting of these lines. And the answer to that question comes from the introduction of the spin angular momentum to the model of the hydrogen atom. So when we introduce the spin into the hydrogen atom, it leads to an interaction, what's called as spin-orbit interaction, and this spin-orbit interaction becomes a foundation to understand the fine structure of hydrogen atom. So what fine means here is you have the splitting of the spectral lines. So that means you can understand the gravity of the model that we have been discussing. The gravity of this model is that it has applications in astrophysics. It has applications in the quantum physics. It has applications in quantum computers. It has applications in quantum dots in nanotechnology. It has applications in lasers. It has many applications that we have surrounding us. And obviously the spin-orbit interaction leads to what we call as the splitting of spectral lines. So what happens here is, what we have L and we have S. So what L does, L exerts torque on S, and what S does, S exerts torque on L, and there is J. So this L exerts torque on S in such a way that it precesses around the J. It precesses along the total angular momentum of the electron. And this S exerts torque on L in such a way that this L precesses around the J, the total J that we have been talking about. So what we have is, we have a precession due to the spin, and we have the precession due to the orbital motion of the electron. And this precession is towards J. And we understand that this J has a dependence. If you take Jz, it is mjh bar, and this mj has different values, and leading us to understand the fine structure of one electron atoms, leading us to understand the splitting of the spectral lines in case of one electron atoms. So this is how the precession leads to all the mechanics that's involved in our problem. So spin-orbit interaction automatically leads to the fine structure. Now we can extend the same basic model, which becomes the basis to understand the problem of Zeeman effect, anomalous Zeeman effect. And what is anomalous Zeeman effect is when you apply a weak magnetic field to a system of atoms, what you find a range of splitting in the spectral line. And this splitting of spectral line is what's called as Zeeman effect. And Zeeman effect can be explained on the basis of this vector model of atom, model of this hydrogen atom. So if I move from here, so what's happening is I can now I would like to I would like to, so my atom was not interacting with anything. There was an interaction within the atom. And within the atom, you have an interaction, and that interaction leads to what's called a spin-orbit interaction. But when I start disturbing it, when I use an external perturbation, when I use an external disturbance to this atom, now what happens, what can be expected? So if we apply an external magnetic field, so when we do that, we apply the external magnetic field. In this case, now what happens is you have this as the external magnetic field. And J, as I have explained, this is my J. And this J is the result of L and S. So this is my L. L is again precessing along J, and this is my S, and S is again precessing along J, but J is precessing along the applied magnetic field. Say this magnetic field is in the direction south. So what we see here, if we try to understand, what's going on here, is this L exerts torque on S, and the torque that you have on S leads to the precession over the J. So there is precession of S over the J. And the reverse is true for the L, because S exerts torque on L, and L is precessing around the J. Now, J is precessing along the applied magnetic field. And what we analyze from this vector model of one electron atom is we obtain a basis to understand the splitting of spectral lines. It automatically leads to the splitting because you have a dependence on Mj, and Mj can have a range of values, and you can have a range of spectral lines. So when you apply the magnetic field on the system, what happens is there is splitting, and this splitting is the result of the precessions and the dependence of the total angular momentum vector on the total magnetic quantum number. And this way it becomes a basis to understand the basic mechanism of Zeeman effect. So vector model is a basis. It's a basis for us to understand the fine structure of hydrogen atom. It's a basis for us to understand the hyperfine structure of the hydrogen atom, where you take into account the spin of the nucleus. So when you take into account the spin of the nucleus, you can further find the splitting of the spectral lines, which is called as hyperfine structure. And the same thing, when you exert an external magnetic field on this system, you have what is called as anomalous Zeeman effect. Now, moving away from the basic understanding of the vector model of an atom, as I said before, this model has a basis in almost in all domains of research in the modern times. It's a strong tool for astrophysics. It's a strong tool for quantum computation. It's a very strong tool of quantum dots that we develop in the laboratories nowadays, where we have quantum confinement, and quantum confinement is closely connected to the spin of the electrons that are present in the atoms. It has a basis in demonstrating the atomic transitions. It has a basis in demonstrating the selection rules in spectroscopy. So with this, I would like to end my talk on vector model of one electron atom, or you may simply say hydrogen atom, or you may say hydrogen-like atoms. Bye.